Hey there, everybody. We're going to look at time dilation a little bit more. Um, kind of worth the time to get used to the different things about which one's the relativistic time and the proper time and all that stuff, and a couple other ways of justifying the ultimate speed limit and even actually justifying why time dilation happens at all is the goal today. So we're going to start out. I'm just going to review over this trip question here about Alpha Centauri is 4.3 light years away, and that's from the Earth's person's point of view. And so we could calculate how long it should get there at a certain speed, and if we calculated how long the trip would seem um, to the people on the trip, right? So um, remember we're going to be seeing something to do with length soon because they recognize like wait, it only took 1.4 years to get there. Everything would seem like normal motion to them while they're traveling, but the trip wouldn't take as long for some reason, so they'd have to kind of see something to do with that, right? So what they'll see, spoiler alert, is they'll see that length contracted. The length that they see that they need to go, they will see as smaller. Think of the muons that hit the atmosphere. They're created in the atmosphere and fly towards, travel down towards the Earth. They manage to get to the Earth before they decay because they see that distance. And so they would see that distance as smaller, right? In order to justify how that's possible. Now, this example here, though, we can introduce or look at a concrete example, like with numbers, to do with the twin paradox. So the spacecraft is traveling for the 1.4 years and so on, but then it turns around and comes back another 1.4 years to return to the Earth, right? So how long did the trip take from the Earth observer's point of view? Well, of course, it would just be the 4.625 or 4.5260 or whatever times 2, right? There and back. And then has the space traveler, aged more or less than the Earthbound coworkers? Well, they would have only aged the 1.4 times 2. They'd only aged 2.8 years, right? And so, although this is, of course, strange and unfamiliar, it is absolutely what would happen. Um, our we have technologies, satellites, and GPS navigation, and so on. Those GPS in particular have super accurate clocks in them, and the time that the signal takes to get from your phone to the satellite, and from your phone to another satellite, and so on, is all used to calculate your location. And those calculations, have to include the effects of special relativity, the fact that time is slower because of the satellite's motion. So we knew this in advance, and the calculations were done, and the satellites were designed and made according to those calculations, and everything worked. There's also, by the way, effects on time due to not being as close to the Earth's gravity, and that's actually even a bigger effect. But again, all those calculations were done because we knew about them. I like to think of the possibility of us having discovered special relativity, time dilation, and so on, if we didn't know about it and we had this great idea to do GPS navigation. All of the calculations would have been wrong, right? The locations wouldn't have worked, and we would have been wondering why. And maybe that could have been a way that we would have discovered that time slows down when things are moving fast, and changes to do with position relative to masses due to gravity as well. It's not how our scientific history played out, but I wonder if there are other civilizations out there, if they discovered it that way, or think of the possibility that we could have, right? And it's just kind of neat to think about. Anyways, this apparent twin paradox. Okay, so this is all good, right? The twin paradox comes in where we talk about how, since motion is relative, the Earthbound observer could consider themselves to be moving relative to the spacecraft. Like, instead, the spacecraft stayed still, and somehow the Earth blasted off and went away and came back, and so on, right? And so this would be, of course, a paradox, since they can't be both older and younger than each other. Like, it's one has to actually be younger than the other, right? Or i.e., the space travelers could consider themselves as stationary, and the Earth went away from them and came back. But and so in that scenario, I'm going to reveal that later. But the motion is relative, right? So we'd say, okay, they would see. This is true, by the way. Like, when the spaceship is flying off towards the galaxy or a star or whatever it was. If they had binoculars or a telescope or whatever, and they looked at the Earth, people on Earth as they're going away, the people on Earth would appear in slow motion to them. And then, the picture of the Earth observers observing the people in the spaceship, they would appear slow motion. This is what would happen. So, when they return to Earth, they might incorrectly expect the Earthbound people to be younger than them. So the but is in this is that uniform motion is relative. Okay, so this, how can this apparent contradiction be explained, thus saving, special relativity from an unexplainable, illogical paradox that means it's not true? Well, special relativity is about, is the fact that uniform motion is relative. So the claim of uniform motion relative to the spacecraft is not valid. Like Earth can't be consider itself as uniform motion because an acceleration had to happen, right? Clearly, the Earth didn't accelerate away from the spacecraft and then turn around and come back. Like that's just not what happened. And so the spacecraft is the one that did the moving relative to Earth, and that's what matters, right? So the spacecraft had the rockets needed to accelerate away and then to turn around. Earth did not. So Earth did not accelerate. Earth did not move in this scenario. Okay. The spaceship was the actual traveler, and so they're the ones that actually age less, right? So there isn't a paradox, and it just seems like there would be if you don't understand that the acceleration of the two objects relative to one another is the distinguishing feature, really. So just another time dilation question here for practice. So they're an astronaut, and I like this example because it's very obvious which time's which here, I think. So they're playing a song, right? And it's a 4-minute song. So you're on a spaceship, playing a song. You're not at in motion relative to that, CD player, MP3 player, phone, or whatever you're playing it on, right? So that would be the proper time, of course, right? Because they're not moving relative to the device. Anyway, so proper time, 4 minutes. Okay, so then you're looking for the relativistic time. What an Earth observer, it says, indicate the time measured by both the astronaut in the fast-moving spaceship and the time measured by mission control at home, listening to a radio broadcaster or whatever, listening to it happen in the spaceship, right? So calculations, here's the equation. We know from time dilation, we developed it ourselves. Like it's not magic, right? Put the numbers in, so the proper time and the speeds and so on, the c squareds cancel out, and we get that the song would last an extra 2 minutes, right? Because we'd hear it sort of a little bit in slow motion. It would last extra 2 seconds, right? So, or 0.02, I don't know, I have to do the calculation there, 0.02 of a minute, I have to say, I suppose. Whereas the if the spaceship was going 0.9, 90% the speed of light, that would stretch out to 9.18 minutes, right? So that that 0.02 of a minute of 60 seconds would be 1.2 seconds. So this would be 4 minutes and 1.2 seconds, whereas the 0.18 of 60 seconds is 10.8 seconds. So 9 minutes and 10.8 seconds, depending on whether that meant. Yeah, you know what I mean? Like this, if this is counting like a clock, that could mean 2 seconds, but it depends on what that was meaning. Anyways, so paraphrasing here, of course, mission control would hear the song playing in slow motion. The astronaut inside the rocket would measure the time to be 4 minutes because otherwise they'd know they're really moving. So quote unquote, and that physics experiment can indicate that, right? The aging process, the person would age less too. So using same numbers here, 4 in terms of years instead of minutes, they can do the same calculation, would spit out the same answer, right? If they're going the 9.9c, they would age 9.18 years. They would say, oh man, the trip was almost 10 years. And people on Earth would say, oh, no, it was just, it was just 4 or whatever. Yeah, it was just 4 years. So notice this isn't like an eternal life or endless youth or anything, but it does allow the fast-moving father to return. It just slows time down, right? But it would allow the father to return to Earth someday physically younger than the son. So you'd have to think of how that would work. Like if the sun was 2 years old, and then the trip happens, and it's a 10-year trip, but that experiences is 20 years for the child. The child's going to be 22, and the father was all think of the numbers there. The father's aging slower than the son, right? So you have to just think of how the numbers would work there. Notice that, of course, the father can't end up younger than the son was when they last saw each other, right? It's not time travel. It's people describe it as traveling into other people's future, right? So you come back and you've only aged 4 years, but 10 years has gone by on Earth, right? So you traveled into other people's future. You've only experienced 4 years of life. It's a kind of like time travel, but it's just time travel into other people's future. Um, so that's done there, and then this is just a little bit more about the speed limit business, right? So nothing can go faster than the speed of light. It's the ultimate speed limit, and so on. Um, so we saw justifications of this already with the laser or light beam chasing a ship, and also the relativistic version of E equals mc squared, where we had the best mass and the increase in energy due to the speed. That was the one that was like the Pythagorean theorem, right? It was understandable-ish, but I mean not required for the course. So this conclusion also can come mathematically from the time dilation. So also comes mathematically from the time dilation equation that we developed, right? And if you look at the equation, you can kind of see why, right? So if the speed was c, then that would be c squared would be a 1. So we'd have root of 1 take away 1, which would mean root of 0, which would be 0. That would mean mathematically, if your something managed to go light speed, that the time dilation equation would lead, which is true about the object, would lead to a divide by 0, and you can't divide by 0, and so you can't go light speed. I was never super satisfied with that as a reason. I like these other ideas that we've seen about the light beam chasing the ship and so on. But math has the power to do that. If it can't happen mathematically, and the math represents reality, then it can't happen in reality. There's a lot of ifs there, though. Like if the math represents reality, then it can't happen, right? So what about faster than the speed of light? That would give a negative number. Well, can you do roots of negatives? No, right? So it can't happen mathematically. And since the math represents real life, if it does, right, then that mathematically that means it can't happen. So yeah. So time dilation is real. Video coming at you here, and then we will So as you can see, there's more to it than just the time dilation equation. The loaf of space-time and the angle of the knife thing, there's other calculations later on if you go on further in this. Don't need to worry about it for now, but I just want you to get a feel for, the situation. So I'm going to keep going here.
But if time, like this frozen river,
Time travel would be using gravity, but they could have done this simpler and just to be to a special relativity where they could have just could have gone on a really fast journey, right? So zip out for a year and back for a year at a really fast rate. The year being the time spent in the ship. You come back, 2 years later, and maybe it's 100 years later on Earth or something, right? That's the same kind of effect. Traveling into others' future is what I was talking about before. So, but yeah, later on, just to, I thought I'd include as well the general relativity idea, so you have a good idea overall of things, even though we're not doing any of the calculations to do with general relativity. So
when I return, I'll find myself in the future.
they're not mentioning here. It's just the idea of the physically trying to go through a wormhole if they exist. The gravity gradient would just tear things to shreds. They call it spaghettification. Your head and your feet would experience vastly different gravity forces and so on. So there's physical limitations involved, likely making it not possible, even if wormholes do actually exist. A lot of sort of like speculation going on in this section for sure, but that's fun.
The math hasn't yet ruled it out. We can't decide.
that for you to watch. Find a YouTube link for it. I think there's one in the previous lesson. The part about that my brain still has trouble with, other than all of it, is the idea of the pages of the book. Like, sure, there's a chance they could land in a nice orderly stacked pile in order. Like, that's one out of a bazillion chance of them ways to land, but they still wouldn't be bound together as a book. They'd just be a stack of pages. And the glass, like, sure, you could reverse all of the directions and put them all back together, like, so that they're in that shape, but they wouldn't be attached anymore. So that's the part that I just don't quite follow in the idea of it. But um, yeah, we've seen this example before here about the evidence of this, the life of a muon thing. So I just left it in as a reminder. But the life time slows down to the point where it has time to get there, and then the idea, the also the idea of the length changing from their point of view, we'll see soon as well. Um, I don't even have a link for that one, so I'm not sure how you'd see it. But anyways, skipping that one. The other thing I want to show you is really cool here, the other justification for time dilation itself. So let me get that queued up. So, summary of that stuff there. We remember from previous sections of physics courses, this one in grade 11, that we had componentizing of velocities and so on, right? So, a three-dimensional velocity, is shared between the x, y, and z dimensions, and which we calculated as components, right? So, Einstein suggested that speed or velocity is shared through time also. Think of what he coined the idea of the term, and thought of the idea of space time as being the fabric of the universe, right? So yeah, Einstein proposed that a combination of an object's speed through x, y, z, and time always adds up to the speed of light. Um, so for ordinary objects, slow speeds in x, y, z, of course, right, the majority of their speed is through time. So the idea is that we can link this to the ultimate speed limit and other things to do with time dilation itself, right? So an object's speed through space-time is always the speed of light. Stationary objects move through time at the speed of light. This is just regular passage of time that we're used to. And then the speed, right, this speed of light through time can be diverted to be speeds through space, right? And so the maximum speed possible through any space dimension is the speed of light, because that's all that there is to be able to divert, right? So, and also, of course, speed through time slows. In other words, time dilation happens as the speed is diverted. Okay, so that's a very different way of explaining the why of time dilation rather than just the what, the calculation of the equations and so on, right? And also note, of course, here that something interesting, light travels at light speed, of course, through space, right? X, Y, and Z. And so light speeds through time must be zero. In other words, light doesn't age. And so, think of that could explain how light can travel for millions of years from stars way, way away and not age. Doesn't die, doesn't dim, it just travels, right? So if anybody ever sort of asked about that or thought of that, that's a justification of it, right? So the rest of the pages here you can read through if you want, but it's just a text version of what we saw in the video. The idea of the diversion of speed through dimensions and time. All right, so that is the last bit about time dilation. There's some questions there for practice about it. And yeah, thanks for watching.